Warning, collision imminent. Gravitational anomaly detected. Captain, we're rapidly approaching the XYO black hole for gravitational assist, but our velocity is critically high. Should we change course? No. Hold steady. Full speed ahead. It's remarkable that these bizarre objects even exist. Invisible monsters of the cosmos, black holes, stretch our understanding of physics to the breaking point. They're gravitational giants so dense that nothing, not even light, can escape their grasp. They twist space, warp time, and can swallow stars without a trace. Scientists have spent decades studying their nature, hoping to unlock the secrets hidden at their core. Yet, despite our advances, black holes remain among the greatest mysteries of the universe. So what exactly is a black hole? They're described by Einstein's theory of general relativity. They're distortions in space-time so extreme that there's a region from which light can't escape. The classic example is a collapse of a massive star. The history goes back to 1916, only a few months after Einstein published his theory of general relativity. Karl Schwarzschild showed how space and time are distorted outside a perfectly spherical, non-spinning ball of matter. It's a solution to Einstein's equations. It tells you the distortion of space-time outside a simple model of a star. It turns out that in those equations, if you keep the distortion but remove the star, just leave the mathematics, you have the description of a black hole. It's in there. And interestingly, if you allow the solution to go infinitely far into the past, you get a description that's not only a black hole, but also a wormhole connecting two universes and a white hole on the other end. It's all there in the mathematics from 1916. They are very natural in that sense. The question becomes, does nature actually create such things given that they can exist? That debate continued into the 1930s. A famous paper by Einstein and Rosen, the Einstein-Rosen bridge, proposed a wormhole solution, but it was Oppenheimer and Snyder, just before World War II, who showed that under certain assumptions, a sufficiently massive star will collapse without limit at the end of its life. Once the star exhausts its nuclear fuel and exceeds certain limits, like the Chandrasekhar limit or the Oppenheimer, Volkoff limit, nothing can stop the collapse. There's a beautiful model called the river model of a black hole. It rewrites those equations in a way that lets you picture space as flowing into the black hole. There's a region of space surrounding the collapsed star, where the river of space is flowing at the speed of light inward. That line is known as the event horizon. The river model is helpful because you can see why light can't escape. It's like a fish swimming in a river that's flowing faster than it can swim. The fish stays in place, swimming as hard as it can, frozen on the horizon. That's what happens to light. It's frozen at the event horizon. Inside, space flows faster than light, and anything inside is swept inevitably inward toward the singularity. There's a deeper way to understand this. In general relativity textbooks, the singularity is not described as a place in space, but a moment in time. Penrose diagrams from the 1960s make this clearer. Once you cross the event horizon, the geometry is such that the singularity lies in your future, and you cannot escape it. It's like tomorrow. No matter how we move, we're going there. It's in this sense that space and time become so distorted that they swap roles. This picture was available as early as 1916 for non-spinning black holes. In the 1960s, Roy Kerr found the solution for spinning black holes. Most physicists initially thought black holes wouldn't form. Oppenheimer and Snyder proved otherwise. Roger Penrose in the 1960s definitively showed that they must form under realistic conditions. Today, we have very strong evidence that they exist. At the center of the Milky Way, stars orbit a central object, Sagittarius A*, a supermassive black hole. The Nobel Prize was awarded for this discovery. We also now have two images of black holes from radio telescopes, one of Sagittarius A*, and one of the black hole in galaxy Messier 87, which is about 6 billion times the mass of our sun. These things exist. The long answer to your short question is, black holes are distortions in space-time, configurations predicted by Einstein's equations, and we now know they are real. They trap light. Now we get into what happens when quantum mechanics is considered. But that's another story. Captain, well, this didn't work out like last time, now did it? Response, Yeah, but this is a different animal. This is Sagittarius A asterisk, a supermassive black hole. Now send the beacon out. Narrator, at the heart of almost every galaxy, including our own, lurks a titan on an unimaginable scale, a supermassive black hole. Millions or even billions of times the mass of our sun, these colossal entities command entire galaxies, orchestrating the motion of billions of stars. They shape cosmic evolution, spew powerful jets of radiation across millions of light years, and light up galaxies from within. Yet their origins remain a mystery. How do supermassive black holes form? Current understanding suggests they form by direct collapse of matter shortly after the Big Bang. Another theory is the merger of many smaller black holes. The model isn't complete. How early galaxies formed and the role black holes played is still not fully understood. That's one reason we built telescopes like the James Webb. In countless science fiction stories, we imagine what happens if you fall into a black hole. Popular culture shows spaghettification, being stretched into strands. But supermassive black holes are intriguingly different because of their immense size. Some scientists suggest you might cross the event horizon without immediately feeling any effects. Could you survive for a moment? Stellar mass black holes, 10 to 30 times the sun's mass, have extreme tidal forces. These become significant before you cross the horizon. But for a supermassive black hole, tidal forces might not be felt until deep inside, near the singularity. You have about a day inside a supermassive black hole after crossing the horizon, depending on its mass, before reaching the singularity. Then, what happens then? Einstein's theory says it's the end of time. But Stephen Hawking showed in the 1970s that black holes radiate and lose energy over time. They evaporate. So it may not be the end after all. Everything may eventually return to the universe. Inevitably, you'd be spaghettified, stretched in one direction, squashed in the other. Your atoms would be torn apart. One of the most fascinating aspects of black holes is their range in size, from stellar remnants to galactic cores. Some supermassive black holes are so enormous they challenge our understanding of physics. How can such objects exist without destabilizing their host galaxies? This leads to the question, how big can black holes get? Their ultimate size depends on how they formed in the early universe, how much material was available to collapse. That traces back to fluctuations in the cosmic microwave background radiation, ripples from quantum fluctuations during inflation, before the Big Bang.